Hey everyone. So today, so basically what's been going on? I've been chasing bugs in the garbage collector. The garbage collector right now in Hadron is a incremental garbage collector, which means that it interleaves what in garbage collector language is called mutator work with so that's the actual interpreter doing work interpreting the language with garbage collection work. And this introduces a number of complexities because the typical like mark sweep garbage collection style, which is where you start at the roots, the known accessible objects, and you scan them, and you scan all the objects there. Looking at transitively until you've scanned the entire reachable graph, and then you everything that wasn't marked as reachable, typically with a coloring. So you start everything's white, and then you mark stuff gray when you're working on it, and then you mark stuff black when you're done with it. Everything that isn't black at the end of that that is not marked. You should have no grays, and everything that's white is unmarked and therefore can be disposed. So that's a typical mark and sweep allocator collector. But the problem is that when you're interleaving mutator work and collector work, then the graph is being changed while you're scanning it. And this is typically handled with what they call a write barrier, which is confusingly, this caused me about a year of confusion before I figured it out. That's not the write barrier that you typically see in like atomic operations. It's a memory sort of fence write barrier. This is a much more conceptual idea, which is the write barrier is basically a function that you need to call, the mutator needs to call when they're changing an object. And what the write barrier does in an incremental collector typically is that it says, hey, you need to rescan this object. And my current incremental collector in Hadron doesn't have a write barrier. There's a way I could easily insert one, but I'm starting to feel like that I want to rewrite this whole thing anyway. This really was just supposed to be a stand-in garbage collector until we could get further down the road and start optimizing. And right now we're not. The whole point of an incremental garbage collector is that it doesn't overly long block the mutator. The mutator doesn't ever have to sit and wait while it does a complete garbage collection cycle. And that's the way it used to work. Like the earliest garbage collectors were, I think, for Lisp. Probably not, but like the ones that I've read about, the very early garbage collectors were for Lisp, and the entire Lisp program would just grind to a halt while the garbage collector was running. And so they would sort of wait until they were almost out of memory, which on machines from the 70s wasn't a long wait. And then they would say, okay, we're stopping the program, and we're gonna just do a complete collection cycle. And if you had a lot of memory, because this scales with the size of your heap, right? So if you have a lot of memory allocated, a lot of objects, then you've got a really complex, large object graph to traverse. It takes a long time, and then you have to go through every pointer that you've allocated and say, like, hey, are you colored? This is the sweep phase, where you basically say, each one of these pointers, you say, hey, did you end up getting marked as reachable? And if not, then you free it, or you add it to the free list, or you delete it, or whatever you're going to do. You can reuse it, you can reclaim it. So, those are very simple garbage collectors, and then people started improving from there with incremental or on the fly, which is like you never stop the mutator at all. You just and then concurrent and parallel garbage collectors. Ones that are doing collection work in parallel or doing collection work while the mutator is running, like on another thread, which requires multi-threaded synchronization. And then there's other techniques like copying collectors, where you make allocations very cheap because everything's just being allocated in a zone, and then you're just going to delete the whole zone, free everything in there, and so anything that's still marked as live, you copy out. Generational garbage collectors, where you're doing that because the observation is that most objects die young. The language tends to allocate a lot of stuff very, very on a short-term basis, and so it makes sense in generational garbage collector to just delete the stuff that like have an easy way to delete objects that are freshly made, and the assumption being that you'll have to copy very, very few things out, and then you can do other garbage collection tricks on the older generations. You don't necessarily have to have a copy collector. And so modern garbage collectors do all of these things. They do concurrent, parallel, incremental, or even on-the-fly garbage collection. Although I haven't seen a working on-the-fly garbage collector. They might be out there, but most of them seem to be, they still need to occasionally interrupt the mutator. And you just say, hey, wait a second, you need to stop modifying pointers for a second while I sort some of this stuff out. So I've been looking at like modifying the existing garbage collector to be like, okay, you're incremental, but I don't know. I kind of feel like I could probably kick out a Stop the World garbage collector this weekend, and I mean, I think that that'll get us through the benchmarks milestone, and we can kind of finally say, hey, we're done. We're gonna move on with our life, and move on to the next phase of project development. Hopefully, right? If not, we'll jump off that bridge when we come to it. But I have long-term plans for the garbage collector, but I feel like, again, like I want a solid foundation that I'm confident in. And I'm not confident in the current code. And I feel like it's going to take a long time to be confident in the current code. Because I wrote it when I really didn't have a clue about incremental garbage collectors that I do now. Which is, this is, how it works, Much of Hadron is designed to be rewritten a couple of times, right? In this like iterative cycle. You get something working, and then you get it correct, and then you start to optimize it. And so we are going to be adding a great deal of complexity to this garbage collector, but I want to build it on a foundation that I'm really confident in, and I want to fuzz it some too. But that's going to be a project for another weekend. Okay, so that's kind of today. I'm trying to write up some design documentation too. But that's kind of sort of as I go, trying to write it in. But let's get into it. Enough talking. And my Stream Deck seems to be totally unable to talk to OBS again, which is delightful and not fun at all. So we're going to try it one more time. Kind of feel like this stuff should work a little bit better. I saw that there's like an open source Python script API available for the Stream Deck. Like you can just kind of do this yourself, and sort of feel like it might work better. Or at least if it's breaking, I can I can go fix it myself. We'll have to see. Okay. But yeah, it's not working. Okay, so rust over. Oh, lovely. What happened here? Camera going. All right. Yay. I'm going to delete that. And again. Okay, there we go. Pardon the interruption. Now I just need to work on the scaling. Ooh. What's the sound? I don't know if y'all take Pilates ever, but I like the instructor who is not typically. I go to a studio Pilates, like just kind of a Pilates factory. But I like that whoever is doing the instruction, who's not doing the exercises, will indicate, woo, like to sort of say like, hey, this is supposed to be hard. Like, you know, if you're struggling, that's okay. They give you permission to be struggling with an exercise. And it's always the same sound. Like every instructor says the same sort of thing, like woo, like it's trying to remind people like, hey, you're having fun. Even though like, you know, you're sitting there and sweating buckets and your legs are shaking like a little baby deer learning how to walk. Stop the world. All right. So we added some stuff to the design doc. I had just notes that I copied out of my Obsidian notebook. But what I wanted to do was just start making a mess. So the first observation is that source runtime GC. This is a good time. I was reading the Rust style guide, and they say don't put a bunch of crap in your mod. You know, actually have a proper. So I'm going to create a new file, new Rust file. It's called garbage collector. And it's going to live here. And we're going to mod sc mod garbage collector. Okay. I'm not quite sure. Oh, this is for the reference counting. I think we can get rid of all that crap, which is lovely to see. All right. Gotta figure out. We can reclaim a lot of this stuff, but we don't need the phase. Yeah. Obstruct garbage collector. Yeah. Very simple. Stop the world. Oh, okay. So, there's just really a, the first thing is I'm tired of having everything in a, like I want things in sets, because I'm tired of having duplicate objects in sets. So the first question is, can I use hash set? For my pointers. I'm just going to grab some crap here. You define GC here, so that's actually interesting. Header, pub structs GC. You're coming here, and you're changing. So I had aspirations of going concurrent. RC ref cell. Can you give an RC a allocation pool? That might actually be a question. Let's open Chrome. And I seem to have lost my camera. Why do I have to reconfigure VLC every single time I want to stream? Like, I don't radically change my my setup. Like, I really don't. Same stuff, same programs, you know. Not that creative a developer. Okay. Rust RC. Pretty. Yeah, you can give it an allocator. Great. Love to hear it. The reason that we do that is that we want to track the allocations. We want to track how much memory we're using, so that this garbage collector will kick off. Yeah, okay. So we need to know about all these things. Use spin RC RC. Use stood cell ref cell. Use crate. Use crate. Runtime SC line, I think. SC line. That's the trait. Use crate. Runtime GC stats allocator. Boom. There you go. Okay. So now that's the thing. So we've got this GC. We know about ref cell, and then we also need to define a header. I don't know. I don't think that I'm, because it's stop the world. I don't think that I actually need the root count. I just need the color. So we'll define header. We're going to define color in a second. We're going to redefine color. Let's bring in color. Yeah. But this is going to change a little bit. Okay. All these things can go in their own. Why are you not just doing all these things in their own files? Yeah. New Rust file. DC. You go in here. The all these things now have to go here. Yes, yes, yes. Header. New Rust file. And color. GH mod header. Okay. And color. Have you already? I thought you already picked up color. No? Okay. New. Color. So actually, pub struct color. We kind of want to redefine this. So as we're pulling stuff out of this, we need to delete all the crap that's in here. Like we could delete color, color. Okay, and then we're gonna pull impl here. Into GC. Okay, borrow mute. Like those things are now wrong. You'll have to rewrite, refactor them. Oh. guys still are compiling. I think we're going to get many complaints. Many complaints from the compiler, but this is principal development. All right, so color. The thing is, in a we were doing this thing where we're like, oh, you know, like we're either, you know, so in a garbage collector, typically when you go through a cycle, you start with everything white, and then you start marking stuff from the roots. You mark the roots gray, you do the graph search, and then as things are being done marked, you've marked all their children because it's like a depth first search. Once you've marked all the children, then you mark the object black, and you're done with it. You take it off the work list. And so pretty, you know, straightforward operation. You don't want to what am I trying to say? You don't, I don't know. The code is, you know, somewhat complex, and you're using this thing. Is it white? Is it gray? Is it black? Right? But the thing is that, you know, at the end of it, like everything that's white can be freed. Everything that's black is part of the live object graph and can't be freed and should be retained. And you're done. But then to start over, to start the next cycle, you would have to go through all of your pointers and color them all white again, right? So that you can start with an all white. You know, everything is presumed to be freed until proven that it can't be freed because it's part of the reachable object graph. So, you know, rather than this order n step for all allocations, I got to step through every single one of them and color them white again. What you commonly see done is that you have your own sort of comparison bit where you sort of say like, hey, what is white for me? Or you have like a white mask or something like that. And by the way, from the perspective of like of like, you know, people and racial politics, this seems really weird that we're like doing this, but I don't know. It's purely academic. So, but like a white mask, like you're trying to determine if something, or a black mask, I don't know though. It's just sort of weird. So I think V8 does something to the extent of like mask for color. So color takes 2 bits. Gray is 0x. It'll be 1 1. Gray is 1 1. White is and then the other 2 colors are relative. Color provides a mask. Color provides a mask, which we and again against the 2 bits, to determine what color, to determine relative color, which avoids a recoloring of all objects at the start of the cycle. So, so this should actually go in the design doc. We'll say something like this. We'll just drop this in. The color bits, prototype collective, color bits, implementation details. And we're going to say something like, so it's like this. Great. The color provides a mask, which we and against the 2 bits to determine relative colors. So, for example, if we define white as as 0B11. Then color is no 0B01. Then if the color is if the color bits are 0B10, then white and 0B10 and 0 0B1 and 0B10 equals 0 0. So this color does not match. The reason we do this is that we often want to know. We sometimes want to know if something is a color match or gray. Or gray. So a and non-zero detection will reveal if a match is present or not, which can often be done in a single opcode. So okay, so basically what we want to say is there's like color and then there's relative color. So I think that pub elam color name so we want pub elam color name, and we don't have a default anymore, and because we don't need it, and then we have a pub struct. Color, which has a single U8, single byte in it. We don't care about anything else. And then we could do color masks. Const black equals 0B10. It's a U8. Const white is the U8 01. Const gray is the U8, and it's equal to 0B11. Okay. And then the default is, you can always start things as white. I think so black, white, gray. I think that we don't need flip anymore. We might need magic gray. What we want to do is mark gray, mark black. And what is white right now? So I think what we want to do is we want to say something like fun mark gray and self and yes, we're gonna get there, and white is U8. I say U8. Is it the U8 or is it just a color? Yeah, give it a color. Make it a color. And color. Okay, boom. So this has to. You don't need white for this. Like this is just. Yeah, you don't need white for this. New. New. White. Return self. Color. No, we're going to say black. What's black right now? We always want things black. Color. Black. Dots. Color. There's no default. You have to know what the relative color is right now. Yeah, okay. Mark gray. We're just going to say self.color equal gray. Mark black and mute. White. So do you want to keep it white or do you want to keep it black? Let's do this. Let's assume. So basically, you're going to mark everything as black, and then you're going to flip everything, and everything that's new is marked as black. And then at the start of the next cycle, you say, okay, I'm redefining black to be white. And so I think that we actually want black here. And then we could just go doesn't return anything. It's just going to go like this. It's going to go like these one-liners. Equal black dot color. There we go. Okay. You never mark anything white, so we have to refactor that. Get name. Get name and self, black and color. And color returns a color name. Okay, and there's a flip too. I think there's a flip. Yeah, we need a flip. Just name. You could say this is black is going to be, let's say that black is what we have defined here. Black, color A, color B, gray. I think it should be A and B avoid naming these. Use black and white. White because they are only those values relative to the current black value. Something like that. A, B. So name. So black is. So first, let's AND it with. If we AND it, if self.color and black.color equals 0, return color name white. If else if self.color equal gray, fuck, equal gray. Return color name gray. Color name black. Okay. There's probably a much more elegant way to do that, and I would love to see how the compiler optimizes that, but I think that'll get us there, right? Early out for a constant compare, I think, is probably faster than a memory access. But anyway, look at the name. There's black, mark gray, match gray. All right, and I think we can even add some quick unit tests, which is lovely to see. New source file. Color unit. Color unit test. Okay. Color unit test. No, this has to go in the main pod. What's your problem? You got an item. Okay. Mod, what do you need? Mod color. Macros, that's web and native for now. It's web and native. A couple things I want to test. So if I have black, reference. Default. So like, how do we bootstrap this thing? And I want to flip name. I would have flipped. Flip. Neat stuff. And I think this is really fun. I think we can just go color. Do we have a 0? You cannot flip gray. Start EQ. Cannot flip. Okay. I think it's just that. It's just like literally, because if you XOR it with 0, then you're just flipping the bits. But that's also just color dot flip bits not bit not bit XOR 0. Core ops bit. Use core ops bit. Bit door and bit and. How come I just can't? 0. U8. Wait. And bit mask. We'll just do a bit mask too. There you go. Alright, so function, so we need a default for color. Default, we're just going to return with A, just to pick a color. Function default is black. Making a new result in black. New black equal default color default assert EQ black dot name and black color name black use color color. Oh, these all need to be pub. Fine. Oh, this is the old logic. Yeah, no. Self.color. And color not equal to 0. There you have it. New 8. Okay. So there. Okay. Default is black. Assert EQ let new new equal color new black and black. What's your problem? No, you get a color and black. Assert EQ black color dot name new dot name black dot flip. Let mute black. Black dot flip. Assert EQ black dot name and black is your name black. Assert new assert EQ white dot name new dot name and black color name white. Change the relative black. Invert the value of relative black. This should not be white. Okay. Flipping colors, I think is a nice one. So let mute black equal color defaults. You gotta spell it correctly. Color black dot flip. We'll do let mutes obj equal color new and black. So these things are always black. Obj.flip. Flip. Okay. Boom. Then we're going to go black dot flip. Now we're going to go obj assert EQ. We already tested this. Obj dot color name and black. Color name white. So this is kind of testing the cycle though. Obj dot mark gray. Assert EQ. Obj dot name and black. Color name gray. Obj dot mark white. Mark black. Assert EQ. Obj dot name and black. Color name black. Black. Boom. Oh. These both need, no, mark gray doesn't need it, but there it is. Okay. Mark black. Sweet. Cool. Okay. So these are some. Then I think we can do. We can do the round trip again, just to make sure that everything's cool. We'll just do name. It's in the namespace, so I don't think we need to call it color name. I think we can just call it name. White. Name black. Name black. There we are. Okay. So this is 2 round trips. Yeah. All right. Tests the normal of coloring through 2 cycles. So all possible states of the capturing all possible states of the color. Okay. Why does mute have to change? I don't think mute has to. Mute.name. I don't think mute. Just new. Name, let new equal color new and black. assert EQ, new dot name, and black, name, black. And this is a macro, not a function. Okay, here we are. Yeah, that's better. And try again. So that's pretty much what I need them for. Header has a color, mod color. Use color, use super color. Great runtime, GC color. Oh, color. It's gonna be like, that's private. Okay. You don't need root count anymore. Say name. We already have it, so I think now we can just drive debug. Color has it. Oh no. Unfortunately, you're just going to get the bit info. For now. You're just going to get the bit info. Okay. We derive that. We derive this. And then we don't have to implement this. And this color is always going to be black. And you don't get to do that anymore either. Yeah, I think actually new gray is fine. Because right now GC takes things. But I don't know if I necessarily want to do that with these new semantics. Just thinking out loud here. We're going to have to come back to this. I think that we're going to need a way of coloring everything black, so that when you flip it ends up white. Impl header. Find new and black, which is an and color. Returns a header. It's just going to be color new black. That's it. Yeah. Unfortunately, we're going to have to change the API around making stuff to go through the garbage collector. because the garbage collector has that kind of sensitive information. It can expose could expose a no, I sort of hate it. I'd rather when it takes it that it says okay. But I mean, ultimately, your allocator is going to be the garbage collector. But it's like, how big of a refactor do you want to do right now? Because every edge new is going to have to go into the garbage collector and be like, hey, garbage collector, allocate me a thing. Which I really don't like. Even though there is a hidden dependency on the garbage collector inside of edge new where it says, okay, I've created myself. So yeah, I don't know. But now we're all making headers. Like, we're all doing header default. Okay. I think actually, no, we'll do info default for a header. Self, actually, I think you can just drive it. No, you don't need to do that. The roots are hard-coded. You shouldn't ever need to, you don't need another root. Objects is carry. What color is right now? Struct color. So color already has a default. The names are there. We just wanted to comment this. Structure used for marking objects as part of the live object graph. Used for marking objects to avoid having to recolor every object, every allocated object on a garbage collector cycle change, we use a relative color scheming where to access the name of the color, we must provide, the caller must provide the current value of black, that way, when a cycle is complete, a new cycle starts to automatically color every object in the graph, every object in the graph white. The collector can flip the black reference color, and then all objects that were black black before are now white relative to the new black reference color. Okay. Boom. Let's color header. All garbage collectors objects must carry. Currently, will perhaps one day be sort of, packed into the collected objects must carry. Will likely one day be integrated into the rest of the system. But I think we can get away with this for now. Okay, so we've got GC header color. I think this guy goes over here. We don't really need a face. The stats is going to be really important. So there's a couple of things that we need to expose. Phase, all this stuff is bullshit. Scavenge state. All right, here we are. Objects. Can you put a GC used in a hash set? Collections hash set. Can you put objects hash set? No, I think you could just use a vec deck again. Use where is that deck? There it is. Objects. Is a vec deck GC. Use GC. Create runtime GC. We don't get GC because we have to go here. Use color use garbage collector. Yep, you're not gonna like that. We'll count that out for now. Color use GC and header GH of use header. There it is. Header. It's redundant. I think we're using anything there. Unit tests. It's fine. Deck. Okay. See. That's it for now. I think we'll take on stuff. Plug and pull. Garbage collector. Oh, it's just info. Oh, dear guy. Yeah, drop will do it. I think no. We still want shutdown. Otherwise, you're going to leak a bunch of stuff. Because they're I think there's a pub fund shutdown. We'll write it. And mute itself. I think it just is going to do something like finalize all objects. Finalize all objects and clear the list. For now, we don't do anything. This is the same. We need these guys, some stats. No, I like to put the derived stuff like right on top. Okay. Final level assets, shut down, executed. Alright, get stats is pretty much the same. Use stats, create runtime gc stats. You could just do pubmod stats, pubuse stats. Oh. Stats diff. Okay. Grab this one and this one. And we'll put them here. We can sort them later. What is the thing? Why is that in SC? Why is that in SC? That's really weird. Where is it? Yeah, because I took it. It's mine now. You need atomic. U64 and ordering. Sync. Atomic U64. Use good sync atomic ordering. Stats allocator. You need a stats allocator. You have one? Okay. Where is it? Oh, that's the use crate. Crate runtime GC stats allocator. Like that. Oh, okay. Just let me get that. Right, cycle count. Okay, so we got that one. Just redoing this API. Now take. This is going to be an interesting one. Put fun take. It takes any type that implements SC-line, which we need to define. I think it is in here. Return GC. take obj equal gc obj rc new in our ref cell new object. That's allocated as the wow. Okay. Yeah. Obj. Let's make them gray. I really want to make them gray. I want to make the default color gray. Gray. But that's going to fail all the unit tests because you need a makes a new color with the same black value as the one applied. For starting a reference color, new reference. Color black, color A. Makes a new reference color with a starting value for black. New reference black. So we have to go fix this color. New reference black. Otherwise it'll fail. Yeah. So default is used only when creating new objects. Colors them to assure they were be recolored. As they will be shortly colored reference black. Okay. All right. You're going to need a reference black. Black. It's a color. No. You do not drive default because you need color. The reference black. Take use the cell our ref cell. This goes for you, and then use the RC, and you need the stats allocator as well. Okay, cool. This doesn't get a printed. Object is private. Yeah, why do we need that crap? I think you could just go here. No. GC. You could say new. This is going to need to be pub. You're doing a lot of stuff with it. Yeah. Okay. Boom. Obj dot. Whoa. Dot borrow mute. Dot header mute. GC header mute. Dot color. Dot color black. Dot color black. So just mark black. Wow. Self dot black. And self dot black. But now we also need to add it to the list of self.objects. Push back. Push back. Obj.clone. That's it. Obj. You actually don't need to keep track of allocated objects. Because that's just the size. And self dot objects dot plane as U64. Okay. There we are. Man, I really wish this doesn't I want it to be a hash set. I really do. I want it to be a hash set. Yeah. I really do. Okay. Dot insert. I think insert true is returned. Yep. There's no add root, remove root. Yep. Do work. Pub fun. So the heuristic now is like we do collections at just hard-coded high water marks. So it's like do work is basically gonna do work and mute self, and then we want a slice of objects. Yeah, they're just GCs. We don't care. Roots and GC, which is a slice of GCs. That's it. Yeah. So for now. Okay, get statistics about the current state of the garbage collector. Finalize and then delete all objects. Finalize and then delete all objects. Finalize and then delete. And then delete all allocated objects. Drop all allocated objects. Drop all allocated objects. Take. Add a SELang adds a compatible objects to garbage collection. Will assert if the object. No, will assert if the object has already been added. Yeah. Do work. I would rather we flip this, but I already feel like that this is too do. Flip the API so that objects are allocated by the garbage collector. Yeah. There we are. Okay. Do work. All right. So now, basic strategy. Possibly determine if they stop the world. If they stop the world incremental. No. Stop the world collection cycle if it is needed, and if so, do one. This may take, this function may take a great deal of time to complete. Okay, finalize all. Then you don't have to, then can drop the hash set, determining, maintaining pointer uniqueness. This function may take a great deal of time. So the current idea is we have a high water mark. Cycle count, last collection at. The number of bytes allocated as the number of bytes allocated by the collector after the last collection cycle completed. Last collection size U64. Force collection increments. Collection increment. So U64, and it is equal to, right now we're going to do it very conservatively. It's 16 times 1024 times 1024. The size of bytes, the size in bytes, increase in bytes allocated before the collector determines another collection is due. Allocation increment. Okay, 16 meg for now. 16 for now. This will require tuning. The high water mark should never go beyond 512. I think we had determined, just very roughly. But 16 bytes in. So do work. Determine if we need to if self dot let allocated bytes, let bytes equal atomic U64 load and stats allocator bytes ordering consistent is fine. If allocated bytes is less than self dot last collection size plus collection increment, return. First we check if we've allocated enough additional memory to force a collection. Check if we've allocated enough. Check if we've allocated enough additional memory to force a collection. Okay. Now we want a collection. Now we want a collection. So we're just going to do it. Forceful collection. Self forceful collection. Boom. And there it is. That's it. Okay. Run the full garbage collection. Run a garbage collection cycle in its entirety. Pub fun, forceful collection, and root self. Oh, and roots, and GC. No, we don't care. Roots. Slice of roots. Okay. Self dot black dot flip. Flip the relative black effectively coloring all allocated objects white in constant time. Coloring all objects white. Color black. Okay, self black dot flip. Okay, so now we can say starting add the roots to the work list. Let mute work list equal I think we should make functions. So there's a mark and then there's a sweep. Mark. Roots. Fun mark. Roots and GC. And flip. What's your problem? No, you can. Sweet. Mark. Sweet. And then we're going to do self.cycle count plus =1, and we're done. And the newly allocated objects, allocated bytes, last collection size equal atomic U64 load stats allocator. This shit needs to go behind an abstraction. bytes. We're just going to make a function here called fun bytes. Bytes returns a U64, and it's just going to do this. And bytes, so that we can just go like this. Pub fun. It's pub. Bytes. Oh. And we're gonna just go. These things are private now. Reclaim bytes. Pub fun. Reclaim bytes. Bytes. For comic. For okay. Bytes. Bytes. Boom. Reclaim bytes. Reclaim bytes. 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 Like that. There. Okay. Boom. Mark. Function mark. No, these things are bad. This is bad. Let's just look at bytes. Say if bytes is less than. And then this thing. Bytes. Tweak and finalize. Okay. We'll get there. Swept full. Mark 4. Started the roots. We started the roots. Add the roots to the work list. Let me work list equal back deck GC new copy from back deck new from slice roots. I don't need to show anymore. Collections back deck. Move from slice roots. Expected U8. Oh, this is a vec deck of DC. How do you do? There's a way to just copy slice. New from way to do this. There's a way to do this. I'm actually a little embarrassed that I don't know how to do it. Just right off the jump. Back, rust, back. New from slice. New back from slice. Slice, leave. Location, guarantees, with capacity, shrink to fit, shrink to, slice, as slice, extend from slice, so you can make a new and then extend it with capacity, slice.size, extend from slice. This seems with capacity, roots.lane, dot extend from slice, roots. Okay, so we just clone everything in the roots in there. Seed the work list. Seed the work list. The work list with the roots, with the supply roots. And then we go like this. We go for int wow. Work list not is empty. Empty. So go through if things are you're going to look at the object, and then you are going to we're going to use the same API to scan that we were already using. Mark okay. You can even do this. Wow, let some let some equal work list dot pop back. Boom. The scar line. No, that's the okay. Yeah, I know this stuff. The actions. For I in for I in mark the object as gray. These objects need to be marked as gray. Mark the roots as gray if they are in the work list. For work list item in work list. For obj in work list. We're going to always call this obj. Obj dot borrow mute dot header gc header mute dot color dot mark gray. Cool. For mute obj in gc work list. Yeah. Okay. Now search the graph and color everything you see. And color it. Dot iter. Okay. Wow, that's uh, so we got the obj range equal 0 dot dot obj dot dot borrow dot selen. Range equal obj dot borrow range for I in range. Okay. Okay, so we're getting it. If let's slot equal obj dot borrow dot sc get I. So here's the thing, like, why do you have to incrementally do this? Why not just sort of say like, hey, give me all your stuff? Yeah, this is awkward. I think eventually to do refactor this, refactor SCLang API to just expose a slice. Let's slot, yeah, broad SC get if let slot object reference inner is we're going to call this child equal slot we need slot. Use crate runtime sc slot. I think slot is just even exposed here. It's so like fundamental. Yeah. Slot. Mark object. Borrow get. Mark index. What? Oh, okay. Child. Let mute slot. Child dot borrow mute dot if lot equal inner mute. Child dot borrow mute dot gc header mute dot color dot mark gray. Mute child. Um, work queue work list dot pushback child. Oh, you have it. Mark it as gray. Okay, so iterate through the object. Iterate through the object. Color everything is gray. Iterate through the object, marking any slots that contain objects as gray and adding them to the work list. Okay, that's it. Now you have done this child, right? So this for loop is mark this object as gray, mark the object as black, and as marking is finished. Yeah. Finished. Obj dot borrow mute dot header mute dc header mute dot color dot mark black and self dot black. You need self. This is and mute self. And mute. No, it's not even. That's funny, but it's not even mute. I don't think it's just and self. Because you're not doing anything other than marking objects. Yeah. Far out. Okay. That's the mark phase. That's really it. It's just a DFS. Now sweep goes through all the allocated objects and either either keeps them or puts them in a finalized queue or a finalized vec. Like it doesn't need to be a deck; it's just a vec. Let finalize sweep finalize. Let objects to finalize. Delete list. Delete list. I mean, you could just do sweep finalize. Just do delete list. Why don't you know about these functions? Like, this is a function. There's a while loop. There's a function. This is garbage collector, right? That's the input of garbage collector. Oh, because it doesn't. Yeah, it needs. Oh, because you didn't say self. Mark self dot sweep and self dot finalize, because these things are and self. This one's and mute self. Yeah. And this one's no. And it returns a vec of DC. And this takes a vec of DC. Delete list. Delete list. Delete list. Vec of DC. We'll just call it delete, because that's not a free word. And delete. Oh, okay. Returns a sweep. Go through all the let delete. Let mute delete equals vec new. Delete. Okay. Go through all outstanding allocations and keeping the ones colored black, keeping the black colored ones, the black ones, and adding removing the white ones to a delete list, which it returns. Returning a list of objects to delete. A list of objects to delete. Okay. Yeah. Delete. Okay. New. Let objects equal self dot objects dot to vec into. I know there's a way to just get it as because I don't like we're gonna let's go back and look at you're still see, this is why I got the Elgato's, that I think I've just been showing you my help for the last, like, you know, hour. But now I need Chrome, and so here we are. Okay, so I was looking at Rust hash set. I think there's a way to get a vector from it, though, into vec or something like that. Extract, string, capacity, get, hasher, insert, set, replace, preserve, contain, shrink to, take, capacity. I mean, you could just run an iter through it. And, okay, well, let's actually switch back to Rust Rover. You can see what I wrote. I wrote the first mark phase. Anyway, alright. Self.objects dot iter dot collect dot copied dot clone dot clones dot iter dot collect iter dot clones dot collect. Yeah, we're just gonna blast it into a vector for item in objects, for in objects boom. If to iter, like we're gonna to iter into iter, and then you don't need clone. Like this thing is, there it is. Yeah, this set cannot be used after calling this. Okay. Yeah, so the set is now junk. Objects. Let self dot objects equal hash set new. Self dot objects equal hash set dot new. Like we're gonna replace it. Drain the current list. Move the current list into a vector for processing. Recreate the this. Make a list of. That's pretty obvious what's going on here. Okay, for obj and objects. Obj dot if obj dot borrow dot. You don't even know what it is, do you? Say this is spec GC borrow dot GC header dot color dot name and self dot black equal black name black color first of all, where's color? Is this enum public? Yes, it is. Good. Okay, we did one thing right. Color use great. Color name. Name black. If self.objects.insert obj. If continue match no continue assert obj.gc header color match. You know what? We could just do this. Let's match obj.borrow .gc header .color .name and self .black. Name black. Self.objects.insert obj. Name gray. Assert gray object found after coloring. White. White. Fuck. Oh. Assert. You have to use it. White. Delete dot push back dot push obj. That's it. There you have it. That's the sweet face. So yeah, we're just, if it's black, we save it. It's been colored. If it's gray, we freak out. That's a bug in the marker. Black objects have been marked as live. We keep them by reinserting them to the list, the set. A gray object indicates a bug in the marking code. This is a fatal panic. White objects have not been marked and can be safely deleted. Okay. There. Finalize. Um, the reference count and pointers. Remove all outbound edges to break reference count and cycles, and then delete the object. And then drops the object. Wow. Well, sum obj equal delete dot pop. Or you could just do for obj in delete dot into iter. Yeah. Okay. Self dot okay, so go back. Ooh. We have to go back to GC and look at the finalizing. This step isn't necessary. Yeah. This step isn't necessary. Let range equal 0 to obj.borrow.sc_line. And then we're just saying sc set. Yeah, just for I in range, let slot equal obj.borrow.scget I. What's the problem here? Dot clone. In range. If slot. If let slot object reference dot equals slot. Obj.borrowMute .sc set I slot. Yeah, just drop it. For mute obj. And that's really it. You've just finalized them, so now you're done. Mute obj. Back. Huh. And equals slot and obj.borrow.color.gc header.color.name and self.black equal name white. Oh, child. Where is it? Push back. Child.clone. Okay. Yeah. It has to be white. Like you don't. Otherwise, you're just wasting time. You're like duplicating a ton of objects that you're encountering that are gray, and like you're just going to be stuck in the cycles forever. So they have to be white. If they're black or gray, then then you are and you are unfortunately not there. So I think that's basically the garbage collector, like forceful collection. Yeah, because Dewberg is saying like, oh yeah, have we allocated 16 meg more RAM? If so, I'm going to do a full collection. Otherwise, not. Yeah, so I think I can kill this garbage collector. Bye-bye. Yeah, from here on down. And the phases. Yeah. Oh, this is fun. I like deleting code. We're going to get rid of this too. We're going to get rid of the tracing stuff. I think it really matters. Which means we can get rid of the Perfetto stuff. Clean up a whole bunch of other junk. Boom. The GC unit tests are still cute. Can we put a box here and put them in? I mean, they're like mod color unit tests. Mod color unit tests. Then we go mod garbage collector. Mod garbage collector unit tests. I think they're just called GC unit tests. We should rename them. Rename. Refactor. Rename. Garbage collector unit tests. Switch. Refactor. Okay. Mod. Garbage collector unit tests. There you have it. Okay. No breakpoint there anymore. Unresolved import. Why was Edge there? Use crate runtime sc no gc edge. Yeah. Sc I think it is edge, which is really dumb. Yeah. GC edge. I think we're going to open up SC and pull out. SC isn't needed anymore. SC is deprecated. Like, we don't need it. So I'm going to rename this thing to Edge. Which means here we have mod Edge. Great. Pub use edge. GC EFGH, pub use edge. Pub create. Yeah. Okay. Fine. Got this thing. That's interesting to me that the unit tests already have a thing. Okay, so edge, start with edge. GC ref, no. This is not going to be that. It is going to be a use the cell ref cell. Use good RC. Then we're going to need a use stood RC use stood cell. I think these are going to be use stood cell ref and ref mute. Use stood cell ref mute. GC ref mute, right? These things go in GC, I think. I think these things go into GC. This is where we define the GC. Drop. Not needed anymore. Okay. Yeah. Nope. Okay. Not need anymore. Mute, GC ref mute, drop. We don't need this anymore. Dref, that's a mutable dref. Dref mute, wrapper class, allowing for typed reference coercion. I think this stuff really belongs here. Yeah, there we go. This all goes here. Ref cell borrow, that includes borrow counting. Typed wrapper, that includes borrow counting. Sync, no, ref, let's just ref. Dref, GC ref mute. This is I think it's a ref mute. Ref mute. Mute. Ref mute. Drop this. New target. Dref mute. Yeah, okay. Clean that up. And then we got this thing. I don't think you need those. I don't know why you need a ref cell. Okay. GC, GC, pub use, garbage collector, garbage collector. Garbage collector, garbage collector. There we are. Color, garbage collector. What's left down here? It's all crap. It's all crap. You need use to GC use crates GC runtime GC GC ref. Pub struct GC ref. Pub struct. You need SCLang. Come we not okay. Where is SCLang even defined? Where is the trait defined? Is it in Edge? Core SCLang. Okay. Okay, I'm getting lost. You went over to Edge. You went over to GC. This is in SC or SCLang. Then you have that stuff. And now you're saying GC ref and GC ref mute. GC pub use GC GC ref pub use GC ref mute. Okay. GC ref use crates runtime GC ref mute. Yeah. Now, what else do you not know about? Oh, so you do need to know their implementation details here. That's fine. This is some gnarly shit. Mute. And this stuff is now new ref map. As ref. Borrow. New. Full Pokemon new. Okay. Object is a new ref mute, GC ref mute. New takes an object mute. You're returning that thing. I think Ezref. Where is Ezref? Where's Ezref defined? Right here. Oh, no, that's just the option. Why is it a RC? No, it's not. GC ref is Dref. What did it return? GC ref. Target equal T. Object ref, target ref. And object is now a rep, which is a stick core cell. So like nowhere now are we referring to an arc. It's a RC, ref cell, dying SC length. Like it is. Here they are. Ref mute. Here they are. Okay. No. Oh, because you have this reference map. There we are. Okay. What else? There's no... This whole SC thing is dead. Dead, dead, dead. Oh. Gone. Okay. It's a good checkpoint. Let's try to build. So mad. Yeah, it's SC. Where is that? That's garbage collector RS. SC core. Core. I moved it around because that other thing doesn't exist anymore. It could just be edges. Edges have to be public again. And they're now fine to use. Nope. Except for they may not survive a full collection. So they have to be added to the roots. So. Okay. So our API, which was spooky, just got spookier. But what if we just had a okay. I think I'm taking a break. So I've been streaming for what, 2.5 hours? Yeah, I think that's a good run. But I really gotta pee, and so check on my dog and stuff. But I think I'm gonna try to finish this out today on my own. I think I'm getting close, but you know, that's before I get it to build. So you know. Who knows? But yeah, if you're watching this offline later, thanks for watching. Primarily do this just to keep myself on task, but also I want to be available in case people are interested in Hadron for Q&A, so feel free to drop by. But yeah, otherwise, thanks a bunch, and I will see you at the next one.